Okay, hey folks, I've got two problems up on the board that have to do with the chapter on conservation of momentum, um, whichever chapter that is. What is it, chapter 11 in your book, or is it chapter 9? I'm teaching two physics ones. It's the one without calculus in any case. It's on, I've got the page numbers at least. This is on page 307. And now this is a two-dimensional conservation of momentum problem. It's a good one to see. It's one of the harder parts of this chapter. Now here you've got a picture, and this picture is on problem 73. This is problem 73 worked out for you. You've got three balls that run into each other. This is the center point where they hit. You've got a 40-gram ball moving at 4 meters per second at an angle of 45 degrees, into the fourth quadrant. You've got a 20-gram ball moving at 2 meters per second up the y-axis. You've got a 30-gram ball moving at 3 meters per second along the x-axis in the negative x direction. They all run together here at the center point. So this is before collision. After collision, you've got the three balls, they meld together, they make a single object, and the total mass of the three together, 20 plus 30 plus 40 gives you 90 grams, and what they want is the final velocity. What's the final velocity of those three balls once they run into each other? And in order to do this, we have a two-dimensional problem, so we have to use conservation of momentum twice, once in the x direction, once in the y direction. So the initial momentum in the x must be equal to the final momentum of the x, same thing for the y. So up here, I'm running through it, and something to keep in mind, I'm keeping the units in grams, not kilograms. I'm doing it all the way through, and it's okay, because at the end, the mass units are going to cancel. You'll see how that works. So here's the mass of the object in the upper left corner there, 40 grams, times its velocity of 4 meters per second, times the cosine of 45 degrees. So now this is just the x portion of the momentum of that upper ball there. And then the only other object that has x component momentum would be this one, because this one only has y component, no x. So that's going to be a negative 30 grams, its mass, times its velocity, negative because it's headed in the negative x direction, right? So if you add those together and you keep the units as grams meters per second, you get about 23 grams meters per second. And so that's also the final momentum in the x direction. Initial equals final. Now we do the same thing for the y direction. The initial momentum of the y direction is negative 40 grams 4 meters per second times the sine of 45. The negative sign because this object is headed into the fourth quadrant, so that would have a negative y component, a positive x component, right? And then the only other object with y component momentum would be this object now. This one has none, it only has x component momentum, right? So it's going to be its mass, 20 grams times 2 meters per second. It's headed vertically upward, so you don't have to worry about a sine or a cosine here. And when you add these two terms together, you get negative 73 grams meters per second. And so that's the final y component of the momentum as well. So we found the initial momentum in the x and the final momentum in the x, the final momentum in the y. And now if we want to find the direction of the momentum after the collision, we take the tangent of the final angle, whatever direction the three balls molded together move out at after the collision. And that'll be equal to the magnitude of the final velocity in the y divided by the final velocity in the x. That's just from the definition of tangent. Tangent of the angle is equal to the opposite over the adjacent. So that ratio is negative 73 over 23 from these values here. The units cancel. They're the same top and bottom, so they cancel out. And that ratio is negative 3.18, so the angle will be the inverse tangent of negative 3.18, which turns out to be about negative 72.5 degrees, so that's definitely into the fourth quadrant. Now, if you want to find the magnitude of the momentum, then you take the momentum of the x, square it, plus the momentum of the y, square it, then take the square root. We're just using the Pythagorean theorem here. And if you plug through that thing, you get 77 grams meters per second. So this is the magnitude of the final momentum. By the way, it's also the magnitude of the initial momentum, right? And now if you want to find the final velocity, it's just going to be the final, the magnitude of the final velocity will be the magnitude of the final momentum divided by the total mass of the object now. So that would be the 77 grams meters per second divided by 90 grams. Notice the units are the same here, so they can cancel out. And you're left with the mass units at least, and you're left with 0.85 meters per second. So this, combination of the three balls together after the collision is moving out at 0.85 meters per second. So if you want to express that final velocity vector in polar form, here's the magnitude, 0.85 meters per second at an angle of negative 72.5 degrees. So that's pointing well into the fourth quadrant. So there's an example of a two-dimensional conservation of momentum problem from the back of the book, from the back of the chapter. So now I've got another problem, and I'm not sure which. I think this one has a picture. It's on the very next page. So it's not on page 307, it's on page 308. Look up near the top of the first column, you'll see this picture. Okay, so now that's supposed to be a hand right there. But there's a table, and this is a frictionless table, and on top of the table is a puck, just a disc with a mass m, and that mass is 100 grams, and it's connected by a string through a hole through the bottom of the table. And so this thing is spinning on this frictionless surface and moving in a circular path due to the tension on this line being held by this hand here. And now you pull this down, and as you pull it down, the radius here, by the way, the initial radius is 20 centimeters. The radius decreases until you're at 10 centimeters. So this thing's going to be being pulled down, and what's that going to do to the speed of the rotating mass? It's going to speed up, right? It's going to have a higher rotation speed of higher omega. So what we want to do is find out if we know the initial frequency of rotation is 100 revolutions per minute. So this thing's revolving 100 times around that hole once every minute when the radius is 20 centimeters. Okay, now you pull that string until the radius is only 10 centimeters, and we want to find out what the new spin rate is. It's going to be spinning around that hole faster now, right? It's like when the ballerina pulls her arms in as she's spinning, she spins faster. Or the ice skater, maybe a better example. Okay, so in order to do this problem, we have to use conservation of angular momentum. Remember, that's the last section of this chapter. And here's the symbol for angular momentum. Capital L initial is equal to capital L final. Initial angular momentum is equal to final angular momentum. And that's angular momentum is also equal to the rotational inertia times the rotational velocity. So that's I omega initial is equal to I omega final. So we need to find the initial and final rotational inertia. We'll do that. We need to find the initial rotational velocity. We'll do that in order to find the final rotational velocity, which we can do using conservation of angular momentum. So let's see. The first thing I did was found omega initial, the initial spin rate. We know that it's going around this hole in the center of the table 100 revolutions per minute, and we know that the radius of this hole is 20 centimeters. So what can we do? Well, let's find the speed that it's moving in this circle. Not the rotational speed first, but just the linear speed. Well, to do that, we need the time that it takes to go around, and we also need the distance around. So the time that it takes to go around, t initial, is 1 over the frequency. So 1 over 100 revolutions per minute would be 0.01 minutes per revolution. Now if you multiply by the conversion factor of 60 seconds per minute, 0.01 minutes times 60 seconds per minute gives you 0.6 seconds. So it takes 0.6 seconds initially for this thing to go around the circle one time if it's revolving at a rate of 100 RPMs. Now, the distance around the circle is the circumference of the circle, which is 2 pi times the initial radius. That works out to 1.26 meters. Okay, so in one revolution, the disk travels around a 1.26 meter circumference in a time of 0.6 seconds. So if you want to calculate the initial velocity, the circumference over period, you get 2.1 meters per second. Okay, now we know the velocity, the tangential velocity. Now what about omega, the rotational velocity? Rotational velocity is equal to tangential velocity over radius. So that's going to be 2.1 meters per second divided by the 0.2 meter radius, and that gives you 10.5 radians per second. So now we know omega initial. Omega initial is 10.5 radians per second. Now what about rotational inertia initial? Well, for a point mass revolving around some center point, the rotational inertia is just the mass times the radius of the circle that it's moving around squared, mr squared. And that works out to 40, or 4 times 10 to the minus third kilograms meters per second. The way you get that, take the radius of 0.2 meters, square it, you get 0.04 meters squared, multiply that by 0.1 kilograms, and that gives you 4 times 10 to the minus third kilograms meters per second. And now we can find the final rotational inertia, the only difference being it's the same mass. The radius now, radius 2 is one half as much as radius 1. If you plug those values in, mr2 squared, you get 10 to the minus third kilograms meters squared. Now back to conservation of angular momentum. I initial omega initial is equal to I final omega final. Solve for omega final. It's going to be I initial over I final times omega initial. We know everything on the right hand side here. So solving for the final rotational velocity, you get 42 radians per second. Okay, so it's spinning in its circle 4 times more quickly now than it was initially. So that's an example of a conservation of angular momentum problem, and that's a good stopping point.